Welcome to the program. We're going to get started in approximately 1 minute. I'll tell you what's going on in the background. I am prepping, getting ready. I'm checking my stream health, making sure I've got a good, strong stream to the platforms that I'm going out to. I could be going to YouTube, Facebook, or LinkedIn, or I could be going to all three. I'm just making sure everything is working correctly. Audio looks good, all that jazz. Please don't forget to chat it up. There's a chat box, regardless of the platform that you're watching this on, whether it be YouTube, Facebook, or LinkedIn, you have the ability to enter your comments and your thoughts. Please be mindful everybody gets to see those, but share your knowledge because I think it'll help the program. And watch that chat box because there's a lot of great information in there. And please send me ideas for the future programs. So it's about a minute, so we should be getting started. Thanks. All right, I think I am live. Okay, so give me some chats if you're out there. Welcome to the program. It's been a rough, long day. I had electrical safety workshop meetings. I had customer calls, did a customer presentation or a training partner presentation that we recorded. Made about, I don't know how many cups of coffee in my new wet bar just over there. So thanks and welcome. It is 5 o'clock. Hey, all right, Eaton Tech Talk, TSDN. It's the social distancing network live once again. Felix Sandoval in the house. Hopefully, Felix, you got your shark mug and you're drinking coffee, sitting back, relaxing, got your feet up, got your calculator out, as we are going to get down with ground fault currents. Oh, man. Okay, that's good coffee. Puppy paws. All right, everybody, I'm going to close since I only have to worry about this interface because we are only on YouTube right now. I've posted on everywhere else. Say we've got the 1972 hat trick. Oh, that reminds me, I am going to answer some questions. I got to call those up. So we had a couple questions come up. And I've got to find my Word document. Let me sort by date. Where was it? Can't remember. Nope, that's my ideas. Let me look in my docs. Social media, 1990, it went in. It's not there. Let me look at LinkedIn. It is not there. You know what? I don't know what I did with that Word document. Anyway, we had a few questions. I created a video this morning to address one of those. We got Swartz in the house. We got Felix Sandoval in the house. We got 1972 hat trick. I gotta hear the story behind that name, buddy. I love it though. I love it. Let me find I got to go to my YouTube channel because I've got to find a couple of the questions. There was one question that I know I got on one of my videos here. I'm going to just shut the volume off on my PC because this thing plays. All right, so I'm going to go to Manage. And we're going to go to Comments. Okay. I know I responded. All right, here we go. And it was from Mr. Hattrick. Here we go. Okay. I gotta get my code book. All right. You know what I need? I need one of those dollies that I told my wife this. I gotta build it. Where you see them in libraries where they have the four wheels on them, and then you could just put a bunch of books in them. You know, they put the books in whenever they're putting them away. I need one of those so I can wheel it around. I've got textbooks all over the floor here. All right, so Mr. Hattrick, you had a question. 1970. I'm going to call you 1972, Patrick. The question was around those 5 750 MCM conductors in the race in the raceway. Remember, we had 5 of these, and he pointed out. Question is more geared towards. There it is. He pointed out that. I guess you're from Canada because you mentioned the Canadian Electrical Code. And you said I've given some thought. I know Canadian Electrical Code, parallel conductors in a raceway, and you had the AMF field. So the National Electrical Code includes a section which basically tells us that gives us some rules to follow when we have paralleled conductors. And I am going to try to remember where those were, where that was. Can't remember if it was in 240 for parallel conductors. Oh man, I have a Word document where I already thought about all of this, but it's been a rough day. Anyway, you've got to be careful about what conductors you put in which raceways, and can't put all the A phase and all the B phase and all the C phase. You've got to make sure that you have your A, B, and C, A, B, and C, A, B, and C, and things of that nature. We talk in the National Electrical Code about the length of conductor, the configuration, and the question was whether or not you can. I think you even said it in here. 15 4-inch conductors. Just looking for the code reference so I don't have to think. Hate to have to think. We're going to think enough on all of this other stuff, and for the life of me, I cannot remember that code section. Anyway, if anybody out there in YouTube land remembers, please throw it out there. But we talk about paralleling conductors in a raceway. Maybe it was 300. Let me look at 300. So this 300 is your general requirements. And protection from damage, cables, underground installations, cables in a raceway, concrete, so protection against corrosion, expansion, direct bury, manhole, raceway, concealed wiring. It's odd. Come on, guys. I need you can always come back to it later. Yep, that's what we'll do. I'll come back to that later. But in any case, you got to look at parallel conductors. And the question basically is there enough in there to tell the inspector what to look for, that you can or can't put A, B, and C, or A, all A's, all B's, and all C's, because magnetic influence and all that good stuff. The other part of your question was regarding does the SKM take into consideration the magnetic and influences from the raceway, types of raceway and things like that. Now, from a heating perspective, it doesn't. Not that I'm aware of. But what SKM does do is when you're doing the calculations for fault currents, and when you tell that put that conductor in a raceway, it's going to ask you, is it a metal raceway? Is it PVC? And what it's doing there is establishing the impedance values. Because if you remember in Table 9, Chapter 9, that's where we get our impedance values. And you'll see that the impedance of a conductor is impacted based upon if it's in steel conduit, aluminum conduit, or PVC. And for the most part, it's the reactance, but in some cases the resistances are different as well. In fact, if you look at Table 9 and you follow the alternating current resistance for uncoated copper wires, go all the ways down, you'll see all 3 columns are basically the same until you get to Well, 0.82 until you get about to a number 2. There's a little bit of difference between PVC and aluminum and steel, and then it gets a little bit bigger as you get to the larger conductors. You'll see a larger difference. The small conductors, they're all the same basic resistance values. Your X values will change for PVC, aluminum conduits, and then steel conduits. So what I would say is, dependent upon the raceway that you have put in and what you've selected, that's going to impact your impedance values, and that's going to change your fault current value. So that's the only way that I can think of that that it takes into that consideration. What else? There were a couple other questions in regard to. I'm going to try to open up a file here. SERP, data, template, electrical code, Eaton Tech Talk. Let me grab that one. I think that is it. This is the problem when you have 2 computers. All right, so that, but in any case, so this is the nice thing about being live. Spring agenda, breakers, and then let me open that one. Okay, so seeing the IEEE, they calculate heating of raceways underground that are spaced in a specific pattern ratings and is encased in concrete. So I figured it might, yeah. And you know what? It could very well be that the SKM software does some of that math behind the scenes. I've not specifically used it for that, but more than likely you're probably right that they do incorporate something in there. All right, gotta find my SKM key. Gummit, this is. There it is. I gotta plug my. So the SKM software comes with this key. Gotta take that out. Plug that in. All right, here we go. All right, so what we are going to be doing, and I'm going to get SKM up and running. Like I say, it local hardware key is. All right. We're going to be talking ground fault currents now, right? So we are we have our little impedance diagram, and I think last time I showed you how I did the scenarios in SKM. So I created a scenario to get me back into, I think I did, or maybe I talked about it. I don't know. So I created a scenario. If you remember, this is our one-line diagram, and I see that I've got some things screwed up here. So we're going to just move things around a little bit. Drag that down because I've got this conductor. Whoa. This I think conductor is a little bit backwards. Actually, it's this node. You just got to be mindful of the nodes. Okay, so remember, this is our one-line diagram. I've got a utility. I've got a transformer. I got a conductor, transformer, conductor, and see how this is separated out. So what I have to do is I got to go to project. I've got to go to scenario manager, and then go back to original. So I created a scenario called original. I'm going to activate, say yes, because I want to save that. So this is our base project. Okay, so I've got, I did not separate this breaker out. And the reason I think it's important to do that, because I've got a spreadsheet which I am going to share with you. I'll put this up on. In fact, I'm going to do that. I'm going to show you the spreadsheet, and I'm going to walk through this. Do I want to walk through it yet? No, I don't. Not yet. I'm not ready. So what we're going to do is we're going to take this one-line diagram. We're going to confirm our answers. So I got SKM open over here. If you recall, this was our one line. We basically established our per unit, and we converted all of our impedance, all of our components over to a impedance value. So we've got the utility, we've got the transformer, utility, conductor, transformer, conductor, conductor, transformer, conductor. We have bus A and bus B. We've got motor contribution on bus A. And we went through all of how we came up with these values, and we calculated the fault current at A and B by hand, compared that with SKM. So now what we're going to do is we're going to calculate ground fault current. Now, the thing with ground fault current is you'll remember that ground fault currents, what's the device, the CTs that we use on relays, they call them zero sequence CTs, right? Because the circuit breakers, the donut that we put around all three phases, will any current that goes to ground, the angles are the same and they are additive and they don't cancel each other. When you think about phase A, B, and C, think about phase A, B, and C. I am going to do this. Yeah, hopefully this works. Turned on the whiteboard. Let me just double check my whiteboard. Double check Teams. There it is. Okay, it's working. Okay, so I need my pen. Not my Keith Laughlin pen. I need my digital pen. So if we took and we said 100 at an angle of 120, so we did this. This is what we're going to do. This is 100 at an angle of 0. This is 100 at an angle of 120. This is 100 at an angle of 240. Okay. If I take my calculator and I add, I'm not going to try it on there. I don't know if I don't have it. I take 100, and you can do this, at an angle of 120, or at an angle of 0, at an angle of 0, plus 100 at an angle of 120, plus 100 at an angle of 240, I get 0. They all add to 0. So if I put a donut around three-phase conductors, and they are at 0, 120, and 240, they have this angle displacement between phases. When you add them up, you get 0. Now, if there is a slight difference between it, it's not going to be your calculation may be a little bit off with regard to how much current you calculate in the differential. But for the most part, three-phase systems, you're going to have, when you add these three up vectorially, they will be 0. Okay, and if you work this out, so if you work this one out, you're going to have, remember, we can separate these into, we can separate this into this and that, right? We can separate this one into that and that. So the 100 at angle of 120 will be 100 cosine of 120 for the x. Boy, that's bad. We got 100 cosine of 120 will give us my x value. 100 sine of 120 will give me my y value, and I can go on and on and on. So basically what you're doing, I can break this one into an x plus jy. I can break this one into an x plus jy, and what jy is going to be, my y of for this one is actually going to be 0, right? It's going to be an x value, which is 100 plus 0, j0, because I don't go up on the y-axis. And then this guy down here is going to be an x. It's going to be what? A minus x. And this is also a minus x plus a jy, because the vector goes into the positive side on the y-axis, but it's on the negative side on the x-axis. My bottom left-hand side, my 100 at an angle of 240 is a minus x minus a jy. And if you do the math and you add up all your x's and you add up all your y's, you'll come out to 0 and 0. It just works out that way because they are a balanced system, vectorially separated, magnitudes the same. Now, when you think about symmetrical components, because we're going to be talking about symmetrical components, when you think about a three-phase system, what do we do to simplify our calculations? We get things onto a single phase, and then we say, look, if it's, you can multiply it by 3. If we can, we don't have to be complex and try to do things in a three-phase system. You break it down on a phase-by-phase basis, and then you know that whatever you do on phase A, it's going to be for phase B and for phase C. Symmetrical components is very similar. Symmetrical components is a fundamental from an engineer's perspective. It's very important for us from an engineering perspective. In fact, every textbook, the key book that I'll reference is Symmetrical Components by Wagner and Evans. You know what? And I looked this up. This is an expensive book. This is the second one I bought. It's a Wiley and Sons publication. I had my first one. I don't want to say stolen. It was borrowed and not returned, because I don't believe people. I don't think anybody would steal this book. But when I found out how much it cost, now I'd probably think, well, maybe they stole it. But in any case, this is the Bible, in my opinion, for symmetrical components. But if you go to every other book, so this is the Stevenson book. And for power systems engineers, a lot of textbooks. I mean, if you take power systems engineering classes, at least back when I went to school, the Stevenson book was like the prime textbook. So their introduction of this says in 1918, one of the most powerful tools for dealing with unbalanced polyphase circuits was discussed by Fortescue, CL. I don't know if it's Chucky, Charles, or whatever. Fortescue at a meeting of the AIEE, American Institute of Electrical Engineers. Since that time, the method of symmetrical components has become of great importance and has been the subject of many articles and experimental investigations. A really important, and he has a chapter on this, and my only issue with the Stevenson book is there's not a lot of meat. And especially what we're going to do today, it's hard to find a practical example like what we're going to cover today. So it should be fun. Another book. This is another good book. Electrical Power Systems Engineering Problems and Solutions. I bought this. This is by Elvin, Knable. I don't know. I bought it. It's a McGraw book. There's actually a section in here on symmetrical components. Again, not very good practical examples, but the calculations they have you do in here as examples are good exercises. They do an analysis by a couple different methods. Again, a good resource for you if you're into power systems engineering. Good one to find from a library perspective. It's an older book, but and it's very thin, A good book. I gotta read to you. I gotta read to you. I was just going through as I was watching the IEEE Electrical Safety Workshop. There were a couple good books. Symmetrical components. Oh, this isn't it. Here it is. No, this is it right here. This is it. So I bookmarked this. Okay. Symmetrical components. The size of these currents determined. So this is another. This one here. I'll give you the title of this one. I love the old books because they're very. This is Principles. Oh, this is Woodruff. Woodruff. Very good book. This isn't. Yeah, this is Woodruff's book. So this is Principles of Electric Power Transmission. If you're getting into transmission line theory, this is I think it's the Bible. This is the second edition, 1938, but Principles of Electric Power Transmission by L.F. Woodruff, Woodruff. I found this on, I think it was eBay or whatever, and I think I paid maybe $20 for it. Very good book, but hard to find. It says that symmetrical components, the great majority of faults on power systems are of unsymmetrical nature. The most common type being a short circuit from line to ground. That's what we're talking about right there. The system impedances are usually symmetrical throughout its main elements. Generators, transformers, transmission lines, etc. And the load, the fault currents usually unsymmetrical in three phases may be resolved into a positive, negative, and zero phase sequence currents. And the magnitudes of those are based upon the impedances in there. So every one of these references are going to tell you that positive, negative, and zero sequence are independent of each other. And that's important because when we look at the impedance diagram, a common mistake you might make is you're thinking that all I need to worry about is the zero sequence circuit. But in reality, we're going to have to construct the positive sequence impedance diagram, the negative sequence impedance diagram, and the zero sequence impedance diagram. And you know what they do? They all add together in series. And based on the math, because we know that ground fault currents are 3 times, so we have to factor the 3 in and do the multiplication. So we're going to add impedance. Think about what I just said. This diagram, so you gotta follow me now. So remember this impedance diagram. These impedances, C1, T1, and C2, if I'm going to calculate the ground fault current at bus A, I don't just create the zero sequence impedances of C1, T1, and T2 and say, okay, I'm going to take those zero sequence and calculate ground fault current. What I do is I take what you're seeing here is the positive sequence impedances. When we calculate the three-phase bolted fault, that is based upon the positive sequence impedances. Positive sequence and positive sequence, if I think about the 3 sequences. So you have 1, 2. So I'm going to say this is positive, this is negative sequence impedances. I know I have I know I have phase A, phase B, phase C. Counterclockwise, right? A, B, and C. And we know that the distance is 120 degrees, right? And we already talked about that. 120, 240, 0. The negative sequence, very similar, but it's A, B, C, a different phase rotation. They still are 120 degrees apart from each other. The positive sequence goes AC, or if I go clockwise, it's ABC. The negative sequence clockwise is ACB. So you have 2 fields going in opposite directions. If you look at this book, in the beginning of the book, they do a history. The very first section is Introduction and Historical Development. And I love this chapter because it gives you a perspective. And they tell us that the germ of the idea may be traced to early analysis of single-phase motors, I love this, by Ferraris, Lamy, and others in about 1895. Physics, math, this is mathematical 101, this is math 101, doesn't change. So they said, as part of the analysis, it's shown that a field set up in a single-phase motor can be resolved into two revolving flux fields rotating in opposite directions. So they recognize these fields rotating in opposite directions, and those were the positive and negative sequences. Fortescue brought to the table, and others brought to the table, but Fortescue, I think, is probably the first one who really got it out there, brought in the zero sequences where they're not out of phase with each other. They're not rotating like that and out of phase. They're all in phase with each other because they're all going to ground and they all add. And they came up with, they recognized that since they're all in phase with each other, they won't flow through a delta. They'll circulate in the delta, and we'll talk about that because that's important in creating our impedance diagram. So this document this book gives you a really good overview of the historical, and I think that's, I like history to begin with, but I think it's important. The reference that here it is here. I don't know if electric machinery, this is Fitzgerald and Kingsley. This was my college textbook. Actually, it was an edition earlier than this. I bought this one, the 5th edition. There's probably a newer edition. But you know what you can do? Just a word of advice. On your company letterhead, you can write, at least I did back in 93, 94, whatever it was. I wrote to McGraw-Hill, and I asked for the answer key. So I have the answer key to the problems in this. And that tell you what, this is about machinery. So it's electric machinery. They too have a symmetrical component section. Unbalanced phase induction motor occurs when voltages, etc. So they talk about the aspect of symmetrical components in textbooks regarding to motors, transformers as well. So this is my transformer book, and I grabbed a chapter. There's a section in here on three-phase connections. They talk about zero sequence impedances and how that the zero sequence impedance is then simply the conventional. So they talk about the zero sequence impedances of a transformer. So all of these books are going to be referencing symmetrical components, and most power system engineers will get a course in symmetrical components. But if you are in the power world, but you came from a digital electronics world, you probably don't have that background. But there's a lot of references out there. Fitzgerald and Stevenson. Yeah, excellent, Felix. Great references. So positive and negatives. Now, I'll tell you this. When we look at our impedance diagram, positive and negative, this is the positive sequence diagram, and it is also the negative sequence diagram. Symmetrical components is from this is Wagner and Evans. And you know what, Felix, I looked this up. It is an expensive book. This is by Wagner, C.F. Wagner, and R.D. Evans. And with an introduction, so I don't know if you probably can't read that, but there it is, Wagner and Evans. And it is a McGraw-Hill book, and this is relatively new. I got this, I think I got it when I came in. It came out of Canada. Original editions was 1933. It was reprinted in 82, 84, and in 86. They may still be reprinting this, so very good reference. All right. This is the positive sequence, and this is the negative sequence. Now, when you think about what we have, in the positive sequence, we had a impedance of the utility, we had the impedance of a conductor, the impedance of a transformer, the impedance of a conductor, and then you had bus A, right? And what do? We always come back with a voltage source, and this is 1 at the angle of 0 per unit. And those are our impedance. So this is the transformer, this is a conductor. No, I'm sorry. That's the utility, conductor, transformer, conductor. The negative sequence is the same thing. Bus A. That's the conductor, that's the transformer, that's the conductor, that's the utility. There's no voltage source in the negative sequence circuit. The impedances are exactly the same. The zero sequence. Now, and here's what we do. Remember, each sequence, positive, negative, and zero, operate independent. They don't influence each other in any way. We break all of our components down into the positive, negative, and zero sequence. Because they don't impact each other in any way, what I need to do when I draw my circuit, I need to basically connect these in series with each other. So I'm doubling the impedance, right? I'm doubling the impedance so far. I haven't put zero sequence in here, but I'm doubling the impedance of my circuit. You think about it. There's my voltage source, and my other end of this circuit is going to be completed by the zero sequence circuit, which I'm going to draw here. Now, before I do that, let's talk about the fact that because my zero sequence currents are all in phase with each other. And let me see. Just going to take a look. I know I put some work in and I tried to start this discussion. No, I didn't say. Okay, so your zero sequence currents are basically, they're all in phase with each other and they add with each other. But when you think about a transformer and you have a delta Y transformer. I am terrible at drawing delta Y transformers, right? What we know from the theory, and you can do the math and do the calculations, grab your reference books and look at the equations. I think I did go through the equations at one point with the A, B, and C aspect of, I'm gonna look here real quick. Rona Tech. No. So when you look at the way you do your additions of, we already know that A, B, and C, positive sequence, 120 degrees apart, negative sequence, 120 degrees apart, and then your zero sequence, they're all in phase with each other. We know that because of that, your zero sequence currents are going to circulate in this delta because they're not going to be able to go through the delta. Now, that doesn't mean that you're not going to have short circuit current on the line side of this transformer. So if I have a fault down here to ground, because the zero sequence currents won't flow through the delta, that doesn't mean I don't have any current being contributed from the upstream circuit system. It just means that, why that did that. I'm going to have current up here, but I'm going to have an additional current. I'm going to have an additional impedance, which will be a smaller current on the secondary of this transformer, because I'm going to have an additional impedance that I don't have upstream. I'm trying to figure out a better way, a good way to describe this. If you think about how we draw the circuits, when you have a transformer that has I have a system that looks like this, and I have a transformer, and it is a delta Y ground. My equivalent impedance of this will be this. I don't have to worry about any impedances ahead of this transformer, because the ground fault currents won't flow through those impedances, because the delta is an isolation from the rest of the circuit. So if I look at my impedance diagram, this is my utility. I don't include my utility, because why? This transformer here is a delta Y grounded. I won't have any ground fault currents flowing because of my fault on the secondary, bus A. I won't have any ground fault current flowing through that utility. It's not a part of my zero sequence circuit. I won't have any fault current flowing through that conductor. That's not a part of my zero sequence circuit. Now, the transformer has a delta primary, but it has a Y grounded secondary. If I look at this is my %Z for that transformer. It is a part of my zero sequence circuit because it's a Y grounded. All of my zero sequence currents will go to ground, right? And they will add up when they go to ground. Make sense? Hopefully. Because they're in phase with each other. Now, and because they're in phase with each other, they won't go through that delta. That's isolated. I don't include the impedances upstream. So my zero sequence circuit will include the transformer and the conductor, and I'm going to put a little 0 down the bottom. The zero sequence impedance of the conductor. And in a few of my earlier prep meetings for this, I said I'm researching the percent impedances for zero sequence. Now, what I do know, based upon this book, when you go to the transformer section for symmetrical components, they go through all the different types of components. And they'll tell you in here that the positive, negative, and zero sequence currents are exactly the same. There's no difference. In fact, in this book, which is Bean, Shotgun, Moore, and Wentz on transformers. So it's another one. This is an oldie but a goodie. This is Richard Bean, Nicholas Chackan, Harold Moore, Edward C. Wentz. This is the Transformer Engineering Department of Westinghouse Electric Corporation. And this was published in 1959 from McGraw-Hill in New York, Toronto, London. So if I tabbed this for this discussion, this says that if the secondaries of the transformers are short-circuited, blah, 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 the zero sequence impedance is then simply the conventional short circuit impedance. So they go through all the different configurations. They go through a delta Y ground configuration. They go to a YY transformer. They go to a Y grounded Y. They go to, you wouldn't do a delta delta. I mean, wouldn't make sense. In any case, they go through, what is this? The YY auto transformer. They go through a grounding, a zigzag transformer. My first short circuit study, there was I called it the spider on my drawing. And because I had to ask the PE I was working under at the time, I was like, what's the spider? And he said, that's a zigzag transformer. And that established it was a delta-delta system, 2300 volts on a union carbide plant. And it was a zigzag transformer where they were establishing a ground. So it was a grounded system. And they talk about the grounded transformer and all that good stuff. But suffice it to say, the zero sequence, positive sequence, and negative sequence impedances of a transformer are exactly the same. Now, the conductor zero sequence is different. And I haven't put my finger on it yet. SKM uses a multiplier. And I know I talked about this already. SKM zero sequence conductor. Rid of the whiteboard. So see, it's already been clicked. And remember this, I know I discussed this. They talk about, and there's your magnetic. So 1972, buddy, there's your magnetic. Okay, symmetrical compounds from who? Felix Sandoval. So we got, there's the zero sequence, and there's a multiplier. 1.5898 if it's non-magnetic, 3.1515 if it's magnetic, and they give a different multiplier for the resistance than they do the reactance. Historically, what I've always done was just do 3 times the impedance, because I've got 3 different currents. They're all in the same phase, and I would multiply the impedance by 3 times. But based upon this, when you break down the R and the X, you multiply the R by 3.1515, you multiply the X by 2.4617. I haven't called SKM, and I don't know if they're watching, but sometimes they do, sometimes they don't. But I have to give them a call and ask them where those numbers came from, because I'd love to know the math and go through it. And then maybe I'll put together a little paper and publish it, put it up on my site. But in any case, so the reactance value for our impedance diagram for that conductor is going to be different than the reactances for the positive and negative sequence conductors, based upon the magnetic raceway and the multiplying factors. Again, what I used to do to get me in the ballpark, I would do 3 times. But now I'm going to start using the multipliers that they use. Those guys are pretty smart, and they probably have the math behind and their reasoning on that. So what you would do for this system is, that is your circuit. Okay, you've got to calculate the new value for conductor. That would be conductor 2 in our impedance diagram. All right, Robert from Omaha. Thanks you, sir. Thanks for tuning in. So your impedance, equivalent impedance diagram for this ground fault current is going to look like this. Okay. Now, what we also know is the equation that we are going to use for current. So here's what we'll have to do first, is we will have to add these impedances together. And we know what these are. Remember, and I don't have the I'm going to find the, there it is. Okay, so we're going to work off of the top portion of this. Forget about the motor for now. But that motor would play a role, but a motor, a motor has a delta windings, right? The core, if you modeled it, it would be a delta configuration. So a motor is not going to contribute ground fault, zero sequence. It's going to contribute current, but it's not going to contribute zero sequence. So I would not include the motor in my zero sequence diagram because zero sequence currents will not flow through a delta. And I could probably try to pull together a symmetrical components only discussion to go through the math, but it is really heavy math with A's, squareds, and A is the square root of, it's just, it gets heavy real quick. But suffice it to say, zero sequence currents will not flow through a delta, so I wouldn't model the motor in my zero sequence current in my zero sequence circuit, but I would model it in my positive and negative sequence. And if, remember, that motor is in parallel with those four impedances. So my diagram, if I wanted to throw the motor in, would look like this, right? The motor would be in parallel with those impedances. I would reduce those, do the parallel reduction, come up with an equivalent impedance, reduce these, come up with an equivalent impedance, so that I basically have that, and that's my circuit. So each, I have to reduce this into a single impedance, and then add all three of those together. Well, we're not going to do that. I want to try to keep things at least somewhat simple so that we can do some relatively simple math and run and see what SKM does for us. All right. Total is inductive reactance, capacitive reactance, material resistance, conductor insulation type, and wiring method. Robert, you are way ahead. All right, so that's our impedance diagram. So what we do is we're going to again work on this top portion. We're going to take those four impedances. Now the conductor 2, remember, we're going to have to do this multiplying factor for conductor 2. What's the numbers? The numbers were magnetic 3.1515 for the resistance and 2.4617 for the positive, for the X. So let me see. Do I want to do this? Home, slide, new. So let's do this. Let's do the math to calculate and add the 0.0017 at an angle of 82.88, 0.0003 at an angle of 45. Add those four impedances and give me an equivalent. So I'm going to do it here, 0.0017 at an angle of 82.88, and then 0.0003 at an angle of 45, plus 0.0575 at an angle of 80.76, plus 0.001 at an angle of 66.04, plus. And this is what I get. Well, in case you're doing the math, there it is. What I get is, I'm going to put this in 0.0604 at an angle of 80.41. I wish. some reason, every now and then, my little mouse, my little handheld thing, 80.4124, 80.4124. Now, I know you're probably say, why does he go 4124? But I'm telling you what, the error that you introduce will put you further away from what SKM's doing because they're going out to the nth degree. So I want to at least get somewhere in the ballpark. So Robert, a motor turns into a generator when a fault condition occurs when the field collapses. That's exactly right. What do you have? You have the rotor turning. You have the stator standing still. That rotor, it turns into a generator, but it won't generate zero sequence currents. It will generate positive and negative zeros, positive and negative sequence currents. So we model that motor in the positive and negative sequence circuits, but we don't include it in the zero sequence circuit. So what I got is 0.0604 at an angle of 80.4124. That's the positive sequence. The negative sequence is exactly the same, 0.0604 at an angle of 80.4124. Make sense? Capiche? All right. Now I've got to do my zero sequence. Zero sequence currents or zero sequence impedance. Remember, I take only the transformer, which is 0.0575 at an angle of 80.76, and then the conductor, but I've got to modify my conductor. How do I'm going to just try something here. Quick, yep, I can do this. Delete. I can. So my conductor is 0.0004 plus J 0.0009. Now, what did we say? What did we say about this is conductor 2, right? We said that my resistance has to be, I have to take 3.1515 times 0.0004. So 3.1515 0.0004 times is 0.0013, 0.001. And then for my reactance, I have to take 2.4617 times 0.0009. Don't forget those zeros. 0.0009 times 2.4617 is 0.0022. 0.0022. So my new impedance is 0.0013 plus J 0.0022, which is 0.0013 I 0.0022 0.0026. Why it does that? .0026 at an angle of 59.4208. Now, what do I have to do? Insert new duplicate. I am going to delete all of this. I am going to move this up. Now, my zero sequence, remember, my zero sequence system, my zero sequence diagram is going to include that. That's the conductor we just calculated. The transformer, so this is conductor 2. transformer 1 is 5.0575 at an angle of 80.76 degrees. Okay. So there's my T1. And when I add those two together, 0.0026 at an angle of 59.4208 plus 0.0575 at an angle of 80.76 is 0.0599 at an angle of 79.8554. All right. Capiche? So that's my impedance. So I'm going to take this and I'm going to copy. I'm going to come back up to my impedance diagram and I'm going to paste. Whoa. And I'm going to do an undo. Grab that and move it there. So this is now my circuit. Now what I want to do is I need to combine these three into a single impedance to get to my Thevenin equivalent. So I'm going to take 0.0604 at an angle of 80.4124. Oh yeah, what am I doing? I'm thinking, why are they the same? That's positive and negative sequence. And I'm going to do that 0.0604 at an angle of 80.4124 plus. And then I'm going to add 0.0599 at an angle of 79.8554. And my equivalent impedance, my equivalent impedance is, for my Thevenin equivalent, remember this is V at an angle of 0, that's 1 per unit at an angle of 0. This is 0.1807 at an angle of 80.2278. Does that sound right? Let me just take a look at my little spreadsheet. I do that. Z. I have my R and X. I have my Z. 0.18. Yeah, 0.1807. So at 80.227. Okay. So now the magic. So here's the magic is, remember, I am calculating my ground fault current. So what is current? I have one, this is per unit, 1 per unit at an angle of 0 over 0.1807 at an angle of 80.2278. So I do 1 over. Bam. That comes out to 5.5341. 5.5341 at an angle of negative 80.23. That's all I'm going to do. Okay, now remember what we did. Where are we at in the system? We are at bus A. That's the secondary of that voltage. So we got to go back to our per unit. Where's our per unit at? Right here, 1804.22 is where we're at, right? Now, remember the ground fault current zero sequence. We're going to add this 3 times. So what we're going to have to do is do some multiplications here. But let's take this 5.5341 times 1804 Because remember, base actual per unit is equal to actual over base. Actual equals per unit times the base. My base current is 1804 for bus A. So I have to multiply my per unit calculated ground fault current times 1804. And if I just do, if I do that, so I got to take 5.5341 and multiply that by 1804.22, and that's 9,984.7. So if I go back to my whiteboard, and I'm going to multiply this by 1804.22, but I also have to multiply this times 3. So the way, because of zero sequence, because all 3 currents are in series with each other, right? They're in phase with each other. I have to multiply my current by my per unit calculation. I have to multiply that by 3. So think about what we did. We basically doubled the circuit. If I go up, right? So this was my positive sequence. This is my negative sequence. I basically doubled it because both of those are the same. But my zero sequence isn't the whole circuit. I only include the portion of the circuit to the secondary of the transformer and the transformer. I don't include the impedances up above. So I'm adding all of these together to get a ground fault current. And then I'm going to multiply that by 3 because all 3 of those my zero sequence are all in phase with each other. So I multiply that by 3, and then I will get my actual current. So let's do the math. 5.5341 at an angle of 80.23 negative. Multiply that by 1804.22. Multiply that by 3, and I get 29,954.2 at an angle of negative 80.23. Did you get the same thing? I don't know if you're doing the math with me or not, but that's my 29,954.2. So now we need to go to SKM. Okay. All right, so let's take a look at, remember that's my delta Y ground transformer. There's my conductor. If I go to here and I go to impedances, look where it says 0.0210. What was the multiplying factor? So let's just make sure I have my right model. I've got 0.021 is my resistance. My zero sequence should be, that's your story and you're sticking to it. Amen. 1972 hat trick. Hold on, we're going to take a look. My R zero sequence is 3.1515. So 3.1515 times is 0.0662. So I already did it. So that's 0.0662, 0.048, and it has to be 2.4617. 2.4617 times 0.1182, 0.1182. Okay, so I already did the positive and negative sequence impedance for that. Now, scroll down. I'm going to do a run, balanced, run, Forrest, run. There's bus A. I'm going to scroll over. All right. So my 3-phase bolted fault current was 29,872. My ground fault current is 29,939. What did I calculate? 29,954. 29,939, 29,954 minus, I'm 15 amps off. And that is rounding error. I'm here to tell you that's rounding error. Okay, so I feel comfortable with the math. Now, here's what else I'll do. I created a spreadsheet just for all of you, and I'm going to put this out, and I'll put it into the chat while you take a look at let me just walk you through this. You know what? No. Here's what I'm going to do. I am going to, real quick, I'm going to go up to my Dropbox account. And I know I have a folder called 15-Minute Tech Talk. And I'm going to just copy this up so you have the exact same thing that I do. I put it in Corona Tech. I think I put it in Tech Thursdays. There it is. I'm going to drag this over, and then I'm going to, because it's kind of small, I am going to grab the link, copy link, and I'm going to put it in the chat, Control V. All right, so that should get you the this spreadsheet. So here's what I did. And if you recall, remember I have the system, which this was our 29,872. Let's take a look at SKM. What did SKM say? I had 29,872 for the three-phase bolted fault. Look at that, 29,872. The cat's meow. If you click, there is a ground fault tab. And let me show you what I did in this equation, or in this spreadsheet. All right. I need to take a sip. So here's what I got. There's my utility. There's my KVA base, my voltage base, my I base. That's important. There's my R per unit of the utility and my X per unit. And you can see, remember, I have a utility tab. And this is where I have the equation to give me my real. Actually, I calculate my, with the equation from the Beeman handbook, I calculate the Z per unit and the angle, because we know the angle because we're given an X to R ratio. I convert that into my real and reactive per unit values. And then I have that over here, my real and my reactive. I have my Z and my angle. And for the conductors, I have a conductor tab. In the conductor tab, I've got my conductors 1, 2, 3, and 4, and I calculate my resistance. And what's nice about the spreadsheet is, you know, the calculator introduces some error. So yeah, I'm 15 amps off. That's rounding errors. But I have all of the equations in here to show you how I got the per unit values for, there's my per unit values for each of the conductors based upon the lengths. And then also, I don't have to worry about the motor because we didn't model the motor. The transformer, I've got my transformer impedances, so I have a transformer tab. So you have somebody let me know if you've downloaded that, if it worked. So you have, I have all of my impedance values. Now, I have I created a positive sequence column and a negative sequence column, and you'll notice they are all the same. And this is bus 1. So for bus 1, we did the manual calculation. I could calculate my R and my X and my Z for positive sequence, my R, my X, and my Z, and my angle for negative sequence. The zero sequence, you'll notice that for the transformer, it's the same. But there's my conductor impedances, which I put in the 3.1515 and I put in the 2.4617 up here in the equation. And I have my Z values. And this is my calculating my fault current. So what I did here, if you just do that, I summed all of my, look, I added my J column, my J's, my N's, and my R's. Why did I do that? Because these are all in series. I added all of my R's in the J column for the positive sequence, all of my R's for my negative sequence, all of my R's for the zero sequence, but we didn't include the utility and we don't include the conductor on the primary of the transformer. We only include the zero sequence for the transformer and the secondary conductors for bus A. So I added all of those up. So I have an equivalent R. I have an equivalent X, a Z, and an angle. And then I do my 3 times my base current divided by this impedance. And I come up with 29,940, 29,939. So that's how it's done. Now, how do I take and calculate the ground fault current at bus B? Don't make the mistake of including the zero sequence. Okay, remember, I'm at bus B, which is on the secondary of transformer 2, right? So I'm on the secondary of transformer 2. When I do my ground fault circuit, my impedances just got on the positive and negative sequence. I have, here's what I'm just going to make life a little bit easier. I'm going to home slide new blank. I have my, here's my positive sequence. That's conductor 1. That's T1. That's conductor 2. That's conductor 3. That is T2. And that is conductor 4. That's my positive sequence. What's my negative sequence? Conductor 1, transformer 1, conductor 2, conductor 3, transformer 2, conductor 4. Exactly the same as my positive sequence. Thanks, Felix. Now, my zero sequence. Remember, this is a delta Y ground transformer, transformer 2. Don't make the mistake of thinking that, well, my ground fault, I have to include that conductor 3 and transformer 1 and conductor 2 because that's a delta Y ground, as a Y grounded on the secondary of that upstream transformer. I'm isolated from that. I only, for my zero sequence, everything is short circuit down to T2 and conductor 4. And so my new circuit is that right there. My T2 will be the same impedance as my positive negative sequence. Conductor 4, for zero sequence, I have to multiply the R's and the X. And I do the same math. I add up all of these impedances. I add up all of those impedances. So I have a Z equivalent. I take 3 times base, I base, and divide that by Z equivalent. And that is my ground fault current at bus B. I don't include the impedances in my zero sequence diagram for any of the conductors and transformers on the primary of T2. Why? Because the primary of T2 is a delta, and zero sequence currents don't flow through the delta. I take a look at my spreadsheet that I gave you. So if you look at this spreadsheet, look what I've added in column V for R. I added all of my positive sequence. I added all of the positive sequence, all of the negative sequence, all the ways up, but only the zero sequence impedances of the transformer and the conductor on T2. I don't include the R's and the X's from T1 or conductor 3 or conductor 2, because the zero sequence, my equivalent circuit, zero sequence currents are going to be trapped by that downstream T2 transformer delta, primary delta. Now, if I look at my calculated value in your spreadsheet, in my spreadsheet, you can format that 14,010.45. 14,010.45. Let's go down to that second bus. There's my T2. There's that delta. Love those deltas because they just block those ground fault currents. And look at this, 14, whoop. I love this stuff. I love it when a plan comes together. 14,010.45, 14,010. And I'll bet you, if they gave us some decimals, it'd be 0.45. And the three-phase bolted fault is 12.844. If I go to this, 12.844. Whoop. Roll home. And I'm looking at two different places. 12.844, 12.844. So you have a spreadsheet that you can do wonders with, depending upon how good you are with spreadsheets. You've got all the math. You could create your own calculator. You could do what I did. I have another spreadsheet, which I'll share with you as well. I'll put it up there. I hope I have it here. Hey, look. I might not. I have it here. So here's what I'll do. I'm going to copy it up, but I have a spreadsheet that I can give y'all a copy of. That let me go to Dropbox.com, and while that's loading, I am going to all files, 15-minute tech talk, and I'm going to grab this document and I'll share the link with everybody here in a second. But what I did was I created a spreadsheet using all of this, what you just see, and I let me find it here. Hold on. I believe it's under my selective coordination folder under tools. Transformer, short circuit calculator, final. Let me just double check. So what I did was I took this same math, and you can make your own. You can take a look at this, take a look at the equations. This is it. So I am going to copy this up, Dropbox, and then put the link out there for you. It's uploaded to bring up the chat. Oh, here it is, right here. Do a refresh. I'll put this link up there. Short circuit calculator. Again, use at your own risk. Copy link. Getting a copy. Control C, and I'm going to put this over here. Control V. So this is another one for you that you can use. I'm going to download it too because I don't have it on this computer. Short circuit calculator, and how do I download? I'm going to click on this and say download, and then I'll walk you through it real quick. All right, so this little calculator, it doesn't do ground fault current though. That's the only deal I got for you. So what you do here, and I used a lot of the same exact equations that we just did. I used per unit on this. So I put my utility available fault current. And you know what? Let's take a look. Let's try this. You know what? I don't have the conductor before the utility in between this. So you can modify this. I mean, I don't have it protected. You could add the conductor and then run it and see how it works. But I got the transformer. I got primary. You put the voltage. I put the X to R ratio in. I have my transformer kVA. So if I say 1500 kVA and I do 4160 and 480, which is basically what we got, I got 5.75. There's my 23,789. What did I have? What did SKM have on that? We didn't create that. I do have one conductor. So what did our we had a transformer and we had a conductor. So let's just do it for giggles. So my impedance, ohms per 1,000 foot of that conductor, what was it? Ohms per 1,000 foot. Conductor 1 was what? Whoops. 5 750s. 5 750s. And where did we get the impedance from? We got the impedance from Table 9, Chapter 9. 5 750s. So 750 is X 0.048. Oh, 0.048's there. R is 0.021. 0.021. And I had how many feet? 15 foot. And we had 5 of them. 5 of them puppies. 23,490. What was our what did SKM say? 23,490. 23,490. We got 29,872. 5.75. 29,872. Why is that so different? Oh. 29,872. So I got my transformer 5.75%, 4160 to 480. I didn't work the X to R ratio, so I didn't consider that. If I delete this, I'm gonna delete the. That's what it was. My fault current was really high. So I had 125,000 amps, I think, and the voltage was 4160. Transformer 36. 29,872. I had 15 foot, 5 conductors per phase, 37, was it 125,000? 125,000. So I don't have, make this 100,000. I'm getting like 36,755. I'm not sure why. I think it, oh, there we go. There we go. All right. I had motor contribution. So I have in here in this spreadsheet as well, I have motor contribution at panel 1. So you could add like 100% or whatever. So I got at the end of conductor 1, 29,818. And this was, what did we have? 29,818. I have 29,872. So, and I think, let me change this to 125,000. 29. So there's my transformer. There's conductor 1. I have 30,023. 30,023 as opposed to 29,939. And again, the reason that this is going to be a little higher is because I don't model in that spreadsheet the conductor on the primary of the transformer. And I didn't include the X to R ratio of the transformer. I didn't include the X to R ratio of the utility. Or I did do the utility, X to R. What was the X to R? 8? Take a look. Yeah, X to R is 8. So I'm a little bit high on this by 70 some amps. But again, I didn't model that primary. So you've got 2 tools for you to calculate. This is my both of my little tools that I made for myself, basically. But we calculated the ground fault currents based upon using positive, negative, and 0 sequence currents. And we created the impedance diagram. The only difference that, again, you'll have to think about if you're going to throw the motor in, and you can do the math, and if you do the math and run it, and you want me to run it here on SKM, I'll send you the report and run your example, and you can compare your numbers. But the basically you're just again, you're going to include all of those impedances and only impedance on the secondary of that transformer. That's going to be your added impedance. 3 times I base over your equivalent impedance gives you your ground fault current. Makes sense? Is it too much? Are we hitting the right stuff that you guys, do you think that makes sense? Now, I'm going to really quick try to take a look at some of the questions that I had. Let's take a look at some of the questions. Excellent. Thanks, Felix. And hopefully you can use those. Some of the comments and questions that I had received. Okay. We had 4-inch conduit will carry A phase, B phase, and C phase. I want to come back to that one. Planning on picking up Power System 5th edition. Yep. Why didn't you take 10% away from the impedance value of the transformer? So I should technically, let's talk about the impedance of the transformer. Why? So that transformer has a 5.75% impedance, right? The question basically is, why didn't I take 5.75% of the transformer? I should have. what would I have done? When we calculate short circuit currents, we're looking for interrupting ratings. So both of these transformers should have been modeled at a minus 10%. I didn't do that because I didn't want to complicate the math. And this and from an educational perspective, it's a layers of information. Okay. So when you're modeling for interrupting ratings and short circuit current ratings, you're going to want to take your impedances of your transformers and multiply them by 0.9 minus 10%. Because based on IEEE standards, when I label a transformer, I'm going to label it with an impedance, but I can be plus or minus 10%. If it's a single phase transformer, it's like plus or minus 7.5%. But these transformers are going to be plus or minus 10%. So for the highest fault current, you're going to want to multiply the impedance by 0.9. For the low fault current, you're going to want to multiply it by 1.1. Why would you multiply a transformer impedance to get by 1.1 to get a lower fault current value? For incident energy analyses. When I'm looking at incident energy, I'm going to increase the impedances of my transformer. Assume that my transformer is worst case on the 1.1, the higher impedance value. That'll give me a lower fault current, which could put me into a longer clearing time on my circuit breakers. The next question is, does SKM do that? So let's take a look at SKM. Let's open up the transformer, and I look at impedances. There it is, impedance tolerance. See, I have 0%. I could put 10% in there. So if I put 10% in there, then it's going to use that for my incident energy. And now I did plus or minus 10%. So what's this? 29,872. I'm going to do a run, balance system study. 29,872. 29,872. So it did not use that in my calculation of my bolted fault current because it should have changed. Let's just make sure I have that done. Plus or minus 10%. Wonder why it doesn't do the calculation. I'm gonna have to ask SKM. I would assume that it would run the lower impedance value. Let's take a look at the incident energy analysis. Let's do a custom label scenarios options. So my options are bus, use the maintenance mode, auto update, increase PPE for VCB, for HCB, include equipment devices, overlay, device fails to operate, fault current, percentage of synchronous motor, percentage of generator, include transformer taps, include VFDs, phase shift, all standard, all current, include 5 cycles, exclude. I don't see anything in here for, what was that? No. ANSI, I can use the ANSI process, English. No, I don't see where it counts for it. So you may have to manually, I'll have to do some research. When we get into the arc flash and whatnot, I'll have to do some research to see how SKM, and if you have a tool that you use, how do they incorporate the plus or minus for the transformers and whatnot. So transformer impedance, I would have thought that this thing would use. I'm probably just missing something in here. So in any case, for calculations, you're going to want to use the lower and then use the upper. And if you do that across the board, like for doing arc flash calculations, you'll throw motor contribution in and then you'll take motor contribution out. So Felix, AC equipment compressors also contribute to faults. Yes. So it's a motor right now. Here's the thing that we do when it comes to motors. The rule of thumb is a lot of those motors are going to be smaller, or like smaller than 25 horsepower. So what we will do is, in fact, let me see if I have the, let's see if I have the IEEE color book. The buff book and the red book are two good documents, two good books. So I'm going to open up the red book first, and I'm going to look at motor contribution. Because what we do is we group small motors, and what you could do is say you know there's a lot of compressors out there, there's a lot of 25 horsepower motors or whatnot. You basically sum all of those up and just slap it on a bus. So like that motor 1 that we have here, that could be, that's 300 horsepower of motor. That could be a bunch of 25 horsepower motors that I just sum them all up and slap it on bus A and model it that way. So motor contribution, motor controlling, motor contribution. I'm looking for fault currents, short circuit current calculations. So I'm going to see what there's some rules of thumb that we follow. Motor contribution, okay, types of short circuit currents, base equations. If I had my book here, physically, I'd find it. Impedance elements. Positive, negative, zero sequence, all that good stuff. Basically, the rules of thumb is search for motor. So they give you some assumptions for impedance values. They give you some assumptions for grouping. So it defines 3 induction motors. It recommends omitting the group of motors each less than 50 horsepower. 50 horsepower, and applies multiplying factors 1.2 or 1.0 subtransient impedance of motors in the groups of larger and larger sizes. So it really depends on what you're reading. And remember, when we start modeling motors and whatnot, the motor will have a higher inrush current or a higher fault current contribution for the first half cycle. So what they'll do is, and it'll tail off, right? So what we'll do is we typically worry about the interrupting ratings of circuit breakers, the momentary duties of circuit breakers and whatnot. And so they will incorporate that for the first quarter cycle, first half cycle, so that we know what we're doing and then just forget about it afterwards. So all others 50 horse. So they'll take, because the initial symmetrical RMS magnitude of the current contributed to a terminal short circuit might be 6 times rated for a typical induction motor, they will use 4.8 times the rated current for the first cycle estimated for the large low voltage induction motors, all 50 horsepower and above. Now, again, it says for this motor group, there is a reasonable correspondence of low and high voltage procedures. For smaller induction motors, all motors less than 50 horsepower, a conservative estimate of 3.6 times rated current, that's an equivalent of 0.28 per unit impedance. First cycle assumption of low voltage standards, and effectively is the same as multiplying the subtransient impedance by 1.67. So they'll group motors less than 50 horsepower and just apply a standard impedance value for that group of motors. And depending upon where they're at in the power distribution system, you would lump them on either, like, say, bus A or bus B. And then how we model it is we just put it in parallel with the rest of the circuit. Hopefully that helps you out a little bit there. So the buff book, the red book, I've already mentioned. I don't know where my books are. They're around here somewhere. The IEEE 242 and 141 are the documents. All right. So we calculated ground fault. I gave you 2 spreadsheets. And what else? I'm trying to think if there's anything else I wanted to cover. I just wanted to at least get ground fault currents covered. You understand that when it comes to, and I'll probably try to do a little deep dive on symmetrical components, but to tell you the truth, it's a lot of heavy math and probably not one for a YouTube video. But maybe what I'll try to do is record one and post it so you can read it or watch it as your leisure, because I know at the end of the day at 5 o'clock, I'm spent enough that I probably will make a ton of errors doing all of the detailed math. But that is the that's how you do it. It's how you calculate ground fault currents. You know how to calculate, you know how to create the positive sequence impedance, which means you know how to create the negative sequence impedance, and now you know how to make the zero sequence impedances and what to omit. Beware of your delta Y grounds. That's your isolation. If it's a Y to Y, you include it. You include the other impedances upstream. Very rarely do you see a Y to Y transformer. Okay, you're the most common transformer you're going to come across in the power distribution system is a delta Y ground. So that's how you do it. You just ignore everything on the delta side, model the transformer, model the conductors, but you have to put the conductors in at 3. I used to use 3 times. SKM uses the 2 models, the 2 numbers. I wonder, I'm just going to do real quick. I wonder if SKM zero sequence conductors, what the numbers were again. 3.15, 3.1515, 3.1, and then 2.4617. It's 3.0, it's 4.0. Well, I used to use just 3 times, but apparently, the conductors, the resistance and impedance. Now, I did do some research in this book here, in the symmetrical components book. Let me just go back up. In the symmetrical components book, under conductors. So, and here's what they do is they will typically look at transmission lines. So they'll talk about the impedances of the conductors in a transmission line. Which reminds me, I gotta find my Woodruff book. Here it is. I tell you what, my power systems engineering professor, Jerry Selvaggi, taught us out of this Woodruff book, and I'm telling you, it is a really good book. So if I look at chapter 11 in here, it's called Calculating Fault Currents, Symmetrical Components. It says the great majority of faults on a power system are unsymmetrical. I already read that to you. Transmission line impedances. They'll tell you in here that positive and negative, it says the negative sequence and the positive sequence impedances are equal and are the same as those used in the analysis of balanced conditions. The zero sequence currents are in phase and equal in the 3 lines, and hence must have a neutral return path, such as earth or overhead ground wires. The zero sequence resistance is equal to that of one phase plus 3 times the resistance of the neutral return conductor. The zero sequence reactance is 3 times that of a circuit of 3 wires in parallel as one conductor and the neutral path as the return. So it gets a little bit more dicey when you're dealing with conductors. So it says it's apparent that no precise calculated value of ground return impedance is to be expected because of varying ground conductivity. However, a satisfactory determination can be made by a combination of test procedures and theory, blah, blah, blah. So, and he's got a big, long impedance in here, or calculations. So, and they talk about the height of the conductors off. So that's this one. So it tells me that there's probably some complicated math in for the SKM and why they use what they use, but And if I look at Wagner and Evans, he gets into, and this is a short transmission line. Again, there was zero sequence impedance of a transmission line is an entirely different character from either the positive or negative sequenced impedances. By its very nature, it involves the impedance to currents that are in phase into three conductors, which necessitates a return path either in the earth. We just read that in Woodruff. So everything that I can find when they start talking about zero sequence impedances is related to transmission line. I haven't found anything, and I bet you if I take that same math and that same theory, I can apply that to a conductors in raceway and come up with what SKM came up. But at some point, you have to ask yourself, right? I mean, I understand you're not going to see it on a PE exam. They're not going to ask you that in from a real world perspective. Someone's already worked it out. It's always good as engineers. We try to derive things and understand them. I don't have the time to do that, but if someone else out there wants to try to do the math, I will call SKM and ask them and see if I can get some answers for us. But that's calculating ground faults. All right, 6:49, almost 2 hours. Hopefully you got something out of this session. We didn't dig too much into symmetrical compounds. We know enough to be dangerous, and we are dangerous. So thank you. It says I'm supposed to stand. My watch vibrates and tells me I'm supposed to stand, but I'm not going to do that because we're going to close up shop. So I appreciate you hanging in there, Felix. I hope I got everybody's. We got Robert, probably took off. 1972 hat trick. Oh, 1972 hat trick. I'm going to come back to your question, which is in the code book. I actually did some homework today. I put it in a Word document. I just can't find it. I can't remember off the top of my head the section number, but I will answer that question, and I will do that probably on my next, which I'll probably do it tomorrow. That's what I'll do. I'm going to do a session tomorrow, talk about conductors in a raceway. I'll try to go live around noon or so, or maybe I'll do it in the morning. I don't know, but I'm going to go live. 1972, if you're still out there, where are you located? I don't know what time zone you're in. All right, so I'm good to go. I think I don't have anything else, unless you guys do. So if anybody has any questions, let me know. Otherwise, we're going to close this one up. Maybe go over the exact configuration you were thinking. Yeah, that's what we'll do. We'll take a look at those 5 conductors, how they would go in raceway, and Halifax. Ooh, okay. Halifax. 1972 hat trick. Thanks for sticking in there the whole session. But I'll take a look at coming up with your answer, and I'll do that probably tomorrow. If anything, I'll just go. I'm going to find some time during the day, and I'm just going to go live. And I'll probably go live on all 3, Facebook, LinkedIn, and YouTube. Tony Davidson, thanks for joining. Thanks for hanging in there all the way. I don't know if you came in. And Felix, thank you very much. You got some good tools out of it. Hopefully you got a couple spreadsheets you can play with. And we verified the answers. We know we did the math right. Oh, you've been to Weirton over the last few summers. Great. You should, hey, you know where I'm at. Send me a note. Next time you're in Weirton, West by God, Virginia, we'll go over to DJ's and get some ribs, have some beer, and have a great discussion. All right? All right, everybody. I am spent. It's been a long day. And, boy, I got so many things open right now. I'm just closing everything down. You have the links to the documents. So thanks for hanging in there. Thanks for everything that you guys and gals do for electric safety, for the electrical industry, and all that jazz. So have a good evening. Stay safe. And remember, And remember to stay healthy. M. Swartz, thanks for dialing in. So excellent. Anybody's ever in Weird and West by God, Virginia, look me up. You know my contact information. We'll go get some ribs. DJs. I'm closing up shop. Thanks again, and good night, and have a great evening. And we'll probably answer 1972's question tomorrow. All right, guys and gals, I'm going to close up shop. Take care. And remember, it's all good stuff. Thanks, Gustavo Sanchez. I appreciate you dialing in there. Stay hanging in there, buddy. Awesome. All right. Thank you, Gustavo. Thank you, Miss M. Swartz. Appreciate you. Felix, Tony Davison. Thank you, Tony. All right, we had some good people. James Smith. I don't know if he dialed in or not. I'm looking at some older chats. All righty, guys. Shutting her down.